Welcome. Today we will look at transformation blueprint from Ada to C++. The first thing I want to show here is that this blueprint is hosted on a website and can be accessed by anyone who needs to get insight into the code by using a unique link and user credentials. Uh, This HTML-based static code analysis reveals not only features of the code and shows side-by-side code, but we also can look at the final documentation index, where we see the package structure of the code that was generated. So here I can go into the different levels. I can look at the C++ files, their data elements tables, the data elements within specific file or method, and then the methods under it. Along with those, you'll also see different diagrams and graphs, such as class diagrams, structure charts, data flow diagrams that I will show in a few minutes here. In addition to the code and the package structure, we also do various other analyses. For example, we look at similarity, we look at dead code, the complexity of an application, and have actually a very detailed look into not only the code, the structure, the composition, and the complexity of the application. Here on the right side, you will see a window that is divided by 2 and has the Ada code on the left and the C++ on the right. The great thing here is that each statement or each line really is hyperlinked. So if I wanted to see, where did this for loop in C++ come from, I can click on the little A for Ada, and it will jump to that line in the code right here. So it's really easy for this person that is, getting insights or is being onboarded or is maintaining the application to see how things were transformed and where they came from. We also call this bridge documentation that we provide at the very end of a modernization. And it gives you good insight to onboard people faster and allow them to do their maintenance much quicker. So let's just look at some of the features here. So side-by-side code, of course, all identifiers and type names and types are hyperlinked. So I can actually, click on an actual type or an identifier, and it will jump up in the code and we can see what type it is here. So that's basically that hyperlinking within the code. It's very useful here. And it's useful in the target code too. You'll see we've also taken the comments over and transformed those into new comments. So blocks of comments, we do have two right over here. And in fact, during a modernization, we can actually introduce more comments or artifacts that are desired. So for example, Doxygen comments or Java JDocs comments, Java Docs comments as well. So right now we're in this display board method here of this sample code that I'm showing. On the top, you'll see this blue menu bar that features quite a few useful charts and diagrams. So let's check out the first one here. It's a structure chart. So this one really shows us the structure of the method that we're in, and actually allows us to traverse up and down the call chain. So here, display board is called by 2 other methods and does not call any other methods. So it's an easy way for me to see, where this application is impacted, or what happens if I, depreciate or remove this method. I can see that, 2 other methods need to be, remediated here in order for this to go away. So circle represents that there are no other calls to that method. So try next, I would assume that there are other things that are calling try next. So if I click on this one, it'll jump to the method. Click on structure chart, I can see, okay. Try next is being called by two other methods, an execute methods, and yet again another try next method, and it has various function calls out. And yet again, some function calls have other function calls after them, like this one here, try to update board. But the other ones that I'm seeing here, they're all round or ellipses, I guess, elliptical round features, and those do not have any other methods that are being called from it. So I'll go back to where we were here, and we'll go check out the next graph, which is a control flow graph, really showing the decisions and the control flow within a method. So here I can easily see, without having to look at hundreds or thousands or millions of lines of code, really, what specific method does. So here are decisions, and the great thing again is that these graphs are hyperlinked again. So if I wanted to see this decision, where it is in the new code, on the bottom right, when I click on this, it will jump to that if statement here, or to that for loop. And again, if I want to see what it looked like in Ada, I can click on it and compare it right here. Same with the other decisions here. So this one, the if statement right here, click on the next one, for loop right there. It's an easy way, to visually see what is happening in a method. And the wider this control flow graph is, or the more decisions that are happening in this control flow graph here, the higher the complexity will be. And I'll jump into the complexity index in a second. In addition to structure charts and control flow graphs, we have data flow diagrams. And that one shows data coming into the methods. That's what it would be here on the left. Data where it's being processed and where it leaves the method here too. So it's also a nice way to see the data flow. In addition, we have other UML diagrams. So a cause and effect graph. So this is really showing you the method level rules, not the business rules, but the method level rules that are firing. Again, this is all hyperlinked where we can see decisions and the rules after them. The good thing here is it gives us a visual representation for very complex methods to also make a decision on how to break those up into maybe two methods in order to reduce overall complexity. So I can see here after this decision or after this logic here, there's quite a bit of logic that could most likely be put into a separate file or a separate function itself to reduce the overall complexity of this particular method. Another view of this information is also the state transition table. And this is kind of, the closest thing to what a business rule would look like. So here we have certain causes and then certain effects where we transition from, start to, first level or first to second level here. So as an example, if I is less or equal to 9, that is true, we will fire these two rules, which will transition from state 1 to 2 right here, where the 1 is. And this sender out is happening right here. So it's printing something, pluses and dashes, I guess. So it's an easy way to see the cause and the effect and really the business rule that's happening here. We have state machine graphs as well, and then composite graphs or consolidated graphs like the business rule modeling index, which really show the structure charts, the control flow graph, the code, the state transition table, and also the class diagram here too. other graphs is the, I think the object-orientedness, structure analysis and structure diagram, and then state machine modeling, um, consolidate graphs. Let's go check out the other artifacts that we generate here. And here is another analysis that we do in very large systems that we actually can consolidate using refactoring, either automated or semi-automated refactoring. So here we are looking at a similar records index. So in Ada or other legacy languages such as COBOL or PL1, you actually have a record for each time that you need to use it. In a new language like C++ or Java or C#, you can actually create a record structure that can be reused. So let's see over here. We have two similar records of, I think, size 19 here that are exactly the same but can be consolidated. So for example, I'll just highlight this part here. If I click on the first one, it jumps to that line in the code. If I click on the next one, it will jump to the similar line in this particular code. So if I look at this, I can see, yep, the structure is exactly the same, but the name is, only different. So this is a great candidate, just like the other 192 instances over here, that can be consolidated using our automated or semi-automated refactoring. Here we'll take another one, this Ada package right here. If I click on the next one, I can see it's exactly the same. So perfect candidate for us to consolidate and to give this new record a good, human readable name. Here is another one where we have 13 instances of a record that is the same. So it's probably a type here. Yep. Some kind of time value type. If I click on the next one, there's another type that looks almost exactly like it. So this one is similar, not the same, and could also be consolidated in an automated fashion. We do this not only with records, but also with statements. So, for applications that have been developed and engineered for decades, there's a lot of copy and pasting or not a lot of reuse that is happening. And we have the capability to not only identify such similar code and similar records and similar statements, but also then to refactor such applications to make them leaner and, you have less code that you need to maintain in the new application. I also talked a little bit earlier about complexity here as well. So we are utilizing McCabe's cyclomatic complexity metrics, where 0 right here is easy to maintain and 10 is difficult to maintain. And I can see here that the majority of the application is, fairly easy to maintain, but I see, one method that is above 10. And that one is probably one that has a lot of decisions in it and will most likely give us a headache maintaining it. So let's go check out this method here. Procedure try to update board. If I look at the control flow graph, I can see, yeah, it's pretty wide. It's a pretty wide graph compared to the one I showed earlier. And there are quite a few decisions happening here, also for loops that run over and over. And it really gives us a visual and an easy way to look at the most complex methods and help reduce complexity either in an automated fashion using our solution or of course to manually decide what to do with them. Outside of this, we have also reports index. So we have a metrics reports. It just shows you, how many files did we take in. This was just a very small Sudoku, ADA application that we've modernized, but it gives us, an overall, overview really about how many classes does it have, what's the maximum members in an actual class, the average class statements, really high level information on what this application really consists of. We have various other indices here that are also very important. I would say that some of our customers actually ask us to adapt the blueprints to either show or help them, show something specific or help them do their, daily maintenance work in a more efficient fashion. So as an example, customers have asked us to expose all the exact SQL statements or kicks in COBOL as an example, just to have an overview. Even all of the unreferenced variables that are hanging around in the ether, we can see here that there was a constant here that was never referenced anywhere. So that we could remove. We can also remove dead code during that refactoring exercise and really help clean up the code. Some other ways that customers have used this application or transformation blueprint is also to make changes to their current application. So for example, if I'm looking at a data element and the data element needs to be um, increased, like for example, we have 1,000 stores, but the previous data element only was able to hold 999. So I can actually look at the data elements table for a specific C++ file, and I will see the type and also the field name of such type. So, and good thing here is it actually gives me an easy way to look at the actual data element and where it is being used, where it's being referred to. So, you know, gen, this float random generator that is being used here is used in 3 areas of this application in the Sudoku C++ file, yet again on line number 499 in an expression statement, and then also in a header file here where it's being declared most likely. So I can click on this and I can quickly see and jump to the area where I would need to change that. So if unused global or unused init global needs to change from an integer to a float or long, I can quickly see, wow, there's only one area that I need to change, and it's where it's being defined right here. So that's another use case that our customers have used this blueprint for. I think another way that some of our customers have used the blueprint here is when we look at the code and they are looking to manually rewrite some of these applications or modules within an application, they can actually, quickly see the code and the methods. And, without having to go through all the code, this check one cell function within this C++ file, I can actually go to the control flow graph and base my rewrite on this particular graph, this control flow. Because really, I don't need to look at 500 lines of code if I can see that the decisions are here, and it's really only one if statement, one for loop, yet another if statement, and another for loop over here that this code runs through. So I can quickly see what's going on here. I can rewrite it to Java, C# or C++ if this thing is up for rewrite. In an automated modernization, with our solution, we would do that without having to look at anything, without any manual input, really. And that concludes the demo on the transformation blueprint. Thank you for your time, and please let us know if you have any questions. We're here to help and um, make it better to understand the code and the generated code. Bye bye.